So far, we have used the first derivative to understand where a function is increasing or decreasing, and how to find local maximum and minimum values. Now, we are going to go one step further and look at the overall shape of the graph. Concavity describes how a graph is bending. So instead of just going up or down, now we care about the shape. Is it curving upward or curving downward? To understand this idea more clearly, let's look at the formal definition. Let's say we have a function that is differentiable on an interval. If the derivative is increasing, the function is concave up. If the derivative is decreasing, then the function is concave down. Now, let's look at some graphs so we can actually see what this looks like. Let's start with this first graph. Here, the slopes are getting steeper as we move to the right. So f prime is increasing. That means the graph is concave up. Now, looking at the next one, here, the slopes are getting flatter. So f prime is decreasing. That means the graph is concave down. Here is another example. Even though the function is decreasing, notice the slopes are getting less negative, so they are increasing. That means f prime is increasing, and the graph is still concave up. And finally, this last graph, here the slopes are getting more negative, so f prime is decreasing, which means the graph is concave down. So the big idea here is this. Concavity depends on how the slopes are changing, not just whether the function is increasing or decreasing. Now, instead of checking whether the derivative is increasing or decreasing every time, there is a faster way to do this. This leads us to the second derivative test for concavity. Now, assuming that the function is twice differentiable, that means we can keep taking derivatives twice without any problem. We can use the following test. If the second derivative is greater than 0, then the function is concave up. If the second derivative is less than 0, then the function is concave down. Let's take a moment to understand why this works. Remember, the second derivative, f double prime, tells us how f prime is changing. If f double prime is positive, then f prime is increasing. Then the function is concave up. If f double prime is negative, then f prime is decreasing. Then the function is concave down. Now, let's step back and connect everything we've learned. The first derivative tells us if a function is increasing or decreasing. The second derivative tells us the concavity. Together, they help us understand the full shape of a graph. Now that we understand concavity, we are ready to move on to a very important concept that comes from it. An inflection point is a point where the graph changes concavity. So this is where the graph switches from concave up to concave down, or from concave down to concave up. Let's make it more precise. A point a comma f of a is an inflection point if the function is continuous and the concavity changes at x equals a. Now, let's go through a step-by-step process for using concavity to find this information. Step 1, find the second derivative f double prime. Step 2, find the values of x where the second derivative equals 0 or undefined. These give us the possible points where concavity might change. Step 3, test the sign for the second derivative. This tells us whether the function is concave up or concave down. Step 4, determine where the function is concave up, concave down, and where there are inflection points. Now, let's apply these steps into an example. We're given the function f of x equals negative x to the third plus 3 over 2x squared plus 18x. And we want to find all intervals where the function is concave up and all intervals where the function is concave down. Step 1, find the second derivative. To find the second derivative, I need the first derivative. So first, let's find f prime. F of x equals negative x to the third plus 3 over 2x squared plus 18x. To find f prime, I differentiate term by term. The derivative of negative x to the third is negative 3x squared. The derivative of 3 over 2x squared is 3x. And the derivative of 18x is 18. So f prime is negative 3x squared plus 3x plus 18. Now take the derivative again. The derivative of negative 3x squared is negative 6x. The derivative of positive 3x is positive 3. And the derivative of 18 is 0. So my second derivative is negative 6x plus 3. Now, moving on to step 2. I want to find the values of x where the second derivative equals 0 or undefined. So first, I set the second derivative equals 0. So I have negative 6x plus 3 equals 0. So I have the equation negative 6x plus 3 equals 0. And I want to solve for x. First, subtract 3 from both sides. So I have negative 6x equals negative 3. Then I divide both sides by negative 6. So I have x equals 1/2. So when x equals 1/2, the second derivative equals 0. Now I need to check where the second derivative is undefined. The second derivative is a polynomial. It is defined everywhere. So the only value we need is x equals 1/2. Now, we need to test the sign for the second derivative around x equals 1/2. So start with the number line. And I am going to place 1/2 on my number line. 1/2 splits the number line into two different intervals. This first interval is from negative infinity to 1/2. And this second interval is from 1/2 to infinity. And we want to know if f double prime is positive or negative here, and if f double prime is positive or negative here. So we need to pick a value in each interval and test the sign. First, let's pick a value in this interval. You can pick any value that's less than 1/2, say 0. And I take 0, I plug that into the second derivative. 0 times negative 6 is 0. 0 plus 3 is positive. Next, pick a value in this interval. You can pick any value that is greater than 1/2. Say I pick 10. And I plug 10 into the second derivative. 10 times negative 6 is negative 60. And negative 60 plus 3 is negative. So the second derivative is positive in this region. That means the function is concave up in this region. And the second derivative is negative in this region. That means the function is concave down in this region. And the next step, we are going to state the results. The question asks for the intervals where the function is concave up and intervals where the function is concave down. So the interval where the function is concave up is from negative infinity to 1/2. And the interval where the function is concave down is from 1/2 to infinity. Since the question only asks for intervals where the function is concave up or concave down, so we're done here. But just in case, if they're asking for inflection points, here's how we find it. Look at the sign chart. The function is concave up in this interval and concave down in this interval. Since the concavity changes at 1/2, this means we have an inflection point at x equals 1/2. Inflection point is a point on the graph. So when they're asking for an inflection point, you're looking for the point with x and y coordinate. So the inflection point is 1/2 comma f of 1/2. Now, to find f of 1/2, we plug in 1/2 into f of x. So we have negative 1/2 to the third plus 3 over 2 times 1/2 squared plus 18 times 1/2. And that is 37 over 4. So the inflection point is 1/2 comma 37 over 4.